Rosenbaum from the University of Illinois at Urbana-Champaign. She also received her PhD degree here in EE from Professor Hu's group. Now, she's going to be using some demonstration vehicles and the like, and I believe that students from her same time period are forewarned. So, and her talk is entitled Engineers Solving Problems from ESD to Education.
Okay, do I need a microphone?
Yes.
My class this semester has over 100 students, and I don't use a microphone. We've got 40 in here. So I will put a mic on if you say I need it. Do I need a microphone? No. I didn't think so. All right. Is this a laser pointer?
Yes.
Perfect.
This works better if you want.
This one works better. And I just have one last thing to figure out. There we go. All right, so I'm going to start today by talking a bit about my research on electrostatic discharge protection. Now,
you know, Elyse, I think they're recording and they might be.
But I'll be too loud because I'm used to projecting.
No, you're not.
These are fake pockets. I don't know what to do with this now. Okay. Now, why have I picked this as the topic for the beginning part of my talk? Well, it's because it's a very important integrated circuit reliability problem. And those of us who worked for Chen-Ming in the 1980s and 1990s from him learned all about integrated circuit reliability. So I know that in this audience, there are people who will actually understand what it is I do for a living, and it's just such a thrill for me to be able to tell you. Okay, so as many of you know, components have to go through ESD qualification testing before they can be sold on the open market. And today, many components fail that qualification on the first silicon spin. Now, is this a problem we can get rid of? Not really. ESD is a fact of nature. As long as the materials in the world around us have different electron affinities, which of course they do, there will always be static charging. So we have to live with this. Unfortunately, the technology trends that we all learned about at IEDM this week are making our ICs more vulnerable to ESD-induced damage. For example, the feature size scaling. Also, the ever-increasing data rates at the off-chip I/O. This places tighter and tighter limits on the allowed capacitance. It prevents us from placing large ESD protection devices at the I/Os, which, if we could use them, they would provide excellent shunts for the static discharge current. And then the last problem is we're making bigger chips. We're putting them in larger packages, so the component itself can store more static charge, leading to an increase in the peak discharge current. So I'm going to focus now on a particular kind of ESD, the CDM, the Charge Device Model ESD. And why this particular one? Because it is the primary real-world ESD stress. Now, there's a document published by JEDEC. It's JEDEC Publication 157, which presents a roadmap for CDM protection. And what's shown here, these black lines, those are the recommended target levels. When you do your design, that's the protection level they recommend you design for. Now, this line, that's the factory control level. What that line tells you is what's the magnitude of the ESD stress you should expect to encounter during manufacturing and assembly. And you see, historically, there was a huge margin between the design targets and the factory control levels. So even if you missed your design target, your yield was still probably going to be very high. So now let's look at where we are today. The recommended target level for today's components is 250 volts. And I can tell you the inside word is that many 32 nanometer components cannot pass a 250 volt stress level. So With that in mind, the people who wrote this report, the Industry Council, have recommended that after the 28 nanometer node, the target levels be brought down even lower. Now, as you can see, if we bring the target levels down, that is going to require that the factory controls become even tighter. And it is not a foregone conclusion that that is achievable. But let's say it is. In any case, you see the margin between the real ESD stress level and the design target is going to be very small. If you miss your target, your yield will probably be very poor. So how are we going to meet this challenge? You know, since designs often don't meet the design target, you know, we can't live like that anymore. What are we going to do? My answer is circuit simulation. That's my solution. We should be verifying design ESD reliability before tape out. So let's take a quick look at what that would entail. What I have shown here on the left is a picture of a component, an IC, mounted on a CDM tester. And what's shown here on the right are the capacitive couplings between the component, the integrated circuit, and the tester. So what happens when you mount this device on the tester is all those capacitors are charged to a high potential. And notice those capacitors are located throughout the entire component, on the die and in the package. Basically, all unshielded conducting surfaces of your component get charged up. Then you lower this grounded pogo pin until it contacts one pin or one ball of your package. So then the charge that was stored throughout the entire component will all exit through that one point. What we see from that is this is a full component level stress. It is not isolated to a small portion of the component. And the discharge network includes all of the on-chip protection devices, the power delivery network, the package traces, and the decaps, among other things. So if you were to describe this using if you were to model this to construct a netlist for SPICE simulation, your netlist would contain easily billions of elements. And we could see that's a problem for SPICE-type circuit simulation. So one thing we do have to do is we have to use alternative simulation engines. And we've heard some interesting talks about that today, and I'm looking forward. Where is Xiaolu? There he is. I'm looking forward to talking to him more about that over dinner. But the other thing we have to do is we have to reduce the size of the model, again, for memory reasons and computation time reasons. But we don't want to sacrifice the accuracy of our analysis. So to make the model more sparse without sacrificing accuracy, we really have to understand where and why these ESD failures occur. And in my opinion, the way you get that knowledge is by doing physical experiments. Now, why do I have that opinion? It's because I was trained by Chen-Min Ko, and he trained all of us to be experimentalists. And so I have a very strong bias, and I think it's the correct bias. Oops. But I don't need the microphone. All right, let's try this again. And notice when Chen-Min comes up to give his little blurbs, he doesn't need a mic either. It's professors don't need microphones.
Maybe they don't want to record what I say.
Oh, at the end of the day, they don't want to record my babbling either. Okay, so experiments are the way you get this physical understanding that allows you to build a more sparse or more compact model of your component. Now, I'll just briefly summarize some of my group's contributions to this experimental understanding. We've developed wafer-level CDM testers and then techniques for probing the internal nodes of the circuits during the ESD event. The other thing we've done is we've developed an on-chip voltage monitor. This is a circuit that records the peak potential difference between two nodes in your circuit during the ESD event, and then later on, you power up the chip and you read out the value. The circuit's shown there on the right, and it looks extremely simple. The problem is that even though your component is unpowered during ESD, very large currents are injected into the substrate, which tend to erase dynamic nodes. So you have to be very careful about the way you build that diode and that storage capacitor. Some of our experimental data is shown here. In the interest of time, I'll only discuss this data set. What's plotted here is the voltage stress on the gate oxide of a transistor in the internal core circuitry. This is not a peripheral I/O transistor. This is in the circuit core. And this is the readout from the voltage monitor. So it's the voltage stress as a function of the pin, the external pin on the package that is being zapped by the tester. And what you see is that the induced stress varies very dramatically, very significantly, depending on which pin is zapped. Now, a very interesting comparison might be between the pin labeled VSS2A and the pin labeled VSS2B. Both of those pins connect to the same ground net, and yet they induce different, when you zap to them, they induce different amount of voltage stress in the circuit core. So this sort of pin-dependent voltage stress needs to be captured by the model we eventually developed for our CDM simulations. Okay, so today everybody has focused on how we can improve performance through new transistor technologies. Well, you can also improve circuit performance through new packaging technologies, and that's more of the focus in my research group. And what I show here is a little drawing of a 3D integrated circuit, specifically a 3D DRAM, the hybrid memory cube. And a question you could ask is, do you need to place ESD protection circuits at the inter-die signal interfaces? Now, those inter-die signal interfaces are of tremendous interest to people working on 3D IC because all of the power benefits of this technology come from those signal interfaces. When you integrate die together in this format, you can send signals between the die without having to drive the package parasitics and without having to drive a transmission line. And that allows you to use low voltage CMOS signaling and save a great deal of power. But if you have to place large ESD protection circuits at all of those ports, you will need to expend more power, and you'll lose a lot of the benefits of 3D integration. Now, we've even done some simulation studies to try to quantify that. What these simulation results pertain to is a 3D IC consisting of 2 wide I/O DRAM memory chips integrated with a controller die. Okay, so it's a 3-die stack. And what we're looking at is the channel bandwidth as a function of the transmitter output conductance. This is completely equivalent to the transmitter power. 3 cases. Case 1, no ESD protection at those inter-die signal interfaces. This case, small ESD protection, small voltage clamps, what we call secondary ESD protection. And in this case, we just deploy, the same type of ESD protection circuit we would use at an external peripheral I/O. So what this red line shows is the 266 megahertz bandwidth requirement or target bandwidth for wide I/O DRAM. And you can see the power hit if we use small ESD protection is very minimal. But if you try to use full-size ESD protection, there's a very significant power penalty, so much you would start to question why we do 3D integration. So we, of course, being a reliability group, we've performed the ESD analysis on this technology, and our results show that indeed you do develop potential differences between the die during the discharge, which can present a severe reliability hazard. However, if all of the die connect to a common ground bus, you can achieve sufficient protection by deploying just very small voltage clamps at all of your receiver inputs, which which give you a very small performance or power penalty, as shown here. Now, it's important to note we've done this analysis for the case of a fully assembled component that is mounted on a CDM qualification tester. And you can do other sorts of analyses. You can ask, do you need to place rail clamp protection circuits on all of the die, or do you only need to place the rail clamps on the bottom die, which directly connects to the outside world? Now, for those of you who don't know, a rail clamp is a protection circuit placed between VDD, your power bus, and VSS, your ground bus. We've done the analysis on that, and again, for the case of qualification testing, and it seems that while placing rail clamps on all the die can be helpful, if you're smart about your design, you don't need them. But this does not address the question of ESD events that may occur and probably do occur during the 3D assembly process. You may need to have rail clamps and other protection devices to survive the assembly process. And this is a very, very important topic for the industry to study and solve right now before we go forward with large-scale manufacturing of this technology. And I have a reason for bringing it up here. As a university researcher, I can't really access this very advanced assembly technology. So if there's anyone here working on this, interested in university collaborators, my students are ready and willing. And that wasn't a joke. Okay, so hopefully I've given you a picture on some of what we're working on, and you hopefully are taking away the message that we're working on a subject that is very practical, technologically relevant, and important. Now, as a result of this, my students are very, very aggressively recruited by the semiconductor industry. And it's kind of interesting that they're getting all these job offers without even trying at the same time that there's very high unemployment. Back in November, the number was 7.9% unemployment. So why are there so many jobs for my students, and yet the overall employment numbers are poor? Well, we just finished campaign. And if you listen to the political rhetoric, there's only one reason why unemployment is high, and that reason is that there are not enough jobs. And the reason that there aren't enough jobs is because taxes are too high. That's what we heard during the presidential campaigns. But I really wonder, is that the whole story? Or do we have a mismatch between the jobs that are available, that are open, and the skills of the people who are unemployed? Well, let's take a look at some other articles in the popular press. According to an article in Forbes, the engineer is the hardest job to fill in America. An even more recent article in the New York Times, if you've got the skills, she's got the job. The she, in this case, is the owner of a sheet metal company. So there are jobs there for people with good technical skills. We just simply don't seem to have enough of people with the right training, and that training is engineering. Okay, so why do we have too few engineers? We have too few engineers because too few people are graduating with degrees in engineering. Recent number I found was about 5% of bachelor's degrees are awarded for study in engineering. Now, it's really not that surprising that only 5% of young people are choosing to study engineering when you find out from the NAE that less than 1% of students are exposed to engineering in their K-12 curriculum. So the NAE has written at least one report, probably more, stating very firmly that we need to bring engineering into the K-12 curriculum, and in fact, this recommendation is being adopted by the people who write the educational standards for the various states. Now, it's my opinion that we have to be involved in developing this new curriculum if we want it to be accurate. Now, what do I mean by accurate? One thing, of course, is that the information is technically correct. But the other thing is we want our job to be represented accurately. And who better than us knows what it is we do? Now, according to me, what we do is we creatively apply science and mathematics for the benefit of humankind. And I think we're the ones who need to bring that message out. One last thing, and this will be relevant to the rest of my talk, the NAE has recommended and concluded that when you're trying to teach engineering to children and develop their interest, you need to engage them in meaningful design projects. And now I lost my... Okay, so I am not the only person in the world who thinks that we need to be involved in K-12 engineering outreach. People working in the high-tech industry and people in academia have reached similar conclusions. I'm highlighting an example here from Microsoft, which earned them, I believe it was a front-page article in the New York Times the end of September this year. They are giving some of their employees paid time off from work to go teach computer science classes in high schools. And it's a good program, but there have been a few bumps along the road. For example, primarily because the people going out and doing the outreach have no previous teaching experience. And they don't know how to manage unruly teenagers. Now, if they're young engineers, they don't even have teenagers at home. All of us who are parents of teens have a little practice with this, but your average 35-year-old engineer won't. And they, as a result of their inexperience, they make mistakes, like preparing lengthy PowerPoint presentations and expecting teenagers to sit still through that. So we really can't fault them for any of these little problems because they weren't trained in how to do outreach. And that's something we're trying to address now at the University of Illinois. We are introducing a new class, a graduate level class, to teach our graduate student engineering researchers how to do K-12 outreach. So I've listed some of the elements of our curriculum up here. They're going to learn how to write lesson plans, do assessment. They're going to be introduced to the educational psychology of preteens and teenagers. They're going to learn about diversity in the classroom, and we're even going to teach them how to get funding for outreach activities, how to write proposals. Now, we're not only teaching them pedagogy. There's also a practicum, or a lab part of this class. Once a week, they will go to a middle school and interact with the students. Specifically, they need to prepare a lesson on a real-world problem and challenge the students to solve that problem through design. The students will have 4 weeks to execute the design, and the graduate student researcher will be mentoring them and working with them over that 4-week period. Now, we're not going to be throwing them into the classrooms completely unprepared. Before the first day one of our grad students goes to the classroom, they will have had to present their lesson plan a minimum of 3 times to an experienced middle school teacher who will look at the content and make sure that it's appropriate. After they do their design challenge, it will be assessed. They will have an opportunity to revise it, and then they will present it to another class for another 4-week term. Okay, so this engineering outreach program or class is scheduled for spring 2013, but we're not starting completely cold. We have some experience, some relevant experience before. 2 times we've offered a science outreach training class for graduate students. Now, it wasn't engineering, but it was outreach, it was science. Also, I specifically had an outreach program called Introduction to Engineering that was offered to 5th graders. And because it was my program, it focused on my research. We covered 4 topics: microelectronics, waves, static electricity, and heat. And you might be wondering why the heck I worked with such young children. It's actually important to do outreach before high school. You have to get the kids on that advanced math and science track before they get to high school if you realistically want them to matriculate at a four-year engineering college. Last thing we do is from all of these programs, we take the best of our lesson plans, the best of our demos, and we disseminate them to public school teachers during some summer workshops that we've sponsored. We've done that 3 times now. Okay, so hopefully some of you are thinking, you know, this is a good idea. I'm going to get involved. I want to do engineering outreach. I want to help solve the unemployment problem. So if you do, I'm going to give you a couple of pointers. You need to know your audience's science background. You need to know what they know so that you can communicate to them effectively. You also need to emphasize hands-on active learning over lectures. So to illustrate some of these points, I'm going to show you some of the materials and demos that we used with the 5th graders in our Introduction to Engineering program. So first, what was the kids' background? I talked to the school district science coordinator before we got started, said we'd be working with 5th graders, asked them what they would know. She said they would already know that matter was made up of atoms and that atoms contained electrons, protons, and neutrons. They had also had some exposure to the concept of electricity, and they had built simple circuits with batteries, resistors, and light bulbs. So that was the background of the students we would be working with. Okay, so what did we teach them new? Well, we gave them an introduction to microelectronics. We took apart a cordless phone and looked inside. We looked at what's inside an SD card, and they saw the integrated circuits, and we gave them the right names. This is an IC. We showed them what's inside the IC and where the dye come from. Now, I couldn't show them a transistor. That's too small to see. But I did explain that there were microscopic devices called transistors, which I explained to them as switches. And then we looked at familiar macroscopic examples of switches as shown here. And then we said, okay, switches have just 2 states, open, shut, on, off. And therefore, computers, which are built using these ICs, only understand 2 numbers, 1 and 0. And from that, we taught the kids base 2 arithmetic and Boolean algebra, 10-year-olds. And it was not at all too difficult for them. They learned base 2 arithmetic so quickly. And as for Boolean algebra, they built AND gates and OR gates using pipes and water and valves to do the AND operation and the OR operation. Not at all too difficult. My graduate students who were involved commented that the kids learned base 2 arithmetic more quickly than our undergraduates do. So no, it's really interesting, the cognitive differences between different age people, because there's another question I asked the kids that not one of them got. So let me try it with you, because their teacher had no problem. The adult, she was practically leaping out of her seat, eager to answer this question, but none of the kids got it. Okay, so we learned base 2 arithmetic, and then I said, why did all these different human civilizations scattered throughout the globe all develop base 10 arithmetic?
10 fingers.
That's right, 10 fingers. Obvious to me, obvious to their teacher, not one child figured that out, but they could do base 2 arithmetic. So depending on the age of the people you're working with, their cognitive skills really are different. Okay.
So what does that, which grade does that put Eli in?
Oh, no, he's an adult because he got the fingers. I mean, they really couldn't get it. It was amazing. So the best thing they could come up with is they said, well, one group of people developed base 10 arithmetic, and then it spread all around the world. I'm like, they didn't have airplanes back then, kids. But it was just so interesting working with these children. All right, of course we did ESD. I'm not going to talk about
Rosenbaum from the University of Illinois at Urbana-Champaign. She also received her PhD degree here in EE from Professor Hu's group. Now, she's going to be using some demonstration vehicles and the like, and I believe that students from her same time period are forewarned. So, and her talk is entitled Engineers Solving Problems from ESD to Education.
Okay, do I need a microphone?
Yes.
My class this semester has over 100 students, and I don't use a microphone. We've got 40 in here, so I will put it. We'll use those later.
How big do you?
All right, let's see. Oh, no, much bigger than that. That's not dramatic. Oh, it's too late. Make that one big. As big as, okay, so let's see. Chemming, are you going to be a good sport?
All right.
Okay, this is called, or this is going to be called an electrophorus.
Is my life insurance still good?
That's good.
Okay.
For about 1 minute, could you, this is an insulator. However, human hair and styrofoam have different electron affinities. I believe this one has greater electron affinity, so it is going to get charged negative if he rubs it on his hair for about a minute.
Here? What, half a minute?
Keep going. Is somebody taking a picture? Okay, put it on the table. Okay, now carefully lift this by the insulating handle and just put it on there. Okay, so now hopefully, if he charged the plate well, this pie pan is becoming polarized, with the positive charges being attracted towards the styro plate and the negative charges being repelled. Let's try to ground this plate, allow those negative charges to leave. So I will actually do that. Uh-oh, not good. Okay, this wasn't charged. Okay, this is not good. I did this in my hotel room last night. It was perfect. It works on Jen Chen's hair, I know that. This better not be metallic. Okay, now, to prove that this is charged, why don't you discharge it into your body? Give a little touch. It won't hurt.
Give it a touch.
Did it work?
Yeah.
Yeah. Okay, watch. We could do it again. I put it on here, ground it. Okay, so you see we're charging and discharging repeatedly. Good. So my hair works much better than his. Okay. So let me show you what I have here. I have a capacitor, also known as a Leyden jar. I can go to my... Pardon? Okay, so we have aluminum foil. We have plastic and insulator. I have foil inside too. I've got an electrode here, which is through paper clip chain going to make contact with the inside terminal of my capacitor. So what I want to do is I want Chemming to serve as my ground, and I hope he's grounded. He's going to hold this side and provide a ground, and I'm going to try to charge up the internal, the other plate of the capacitor. Okay. So give me a good, get your hand on all that outside foil. Yeah, okay. Oh, I can't believe I wanted him to do this. Now there's other ways. We can also charge up that PVC pipe and charge the Leyden jar that way. Jen and I had some trouble with that the other night, so we'll try that one next. This one usually is typically very dependable, except when you use Professor Hu's hair. All right.
Doesn't work on big heads.
Okay, this is going to be good. Okay. I didn't hear that. And let me just make sure we got a good amount of charge here. Oh, that's a good one.
Oh, that's good.
Okay, so now we're going to attempt to make some lightning.
All right. Oh, I see that.
Did you see the lightning? So, could you see that, or should we repeat it? Okay, so you can all come up here and try this yourselves, which I actually encourage. So no, this is actually, children have just, because we would have talked about electric fields, they just saw how lightning is made. But now we're going to do the fun stuff. We are going to discharge these much smaller Leyden jars through ourselves. Let me show you how these are constructed. Foil on the outside, a film, which nobody makes anymore, canister. You could use a pill canister, water inside, and a nail. Okay. Same thing. Somebody has to ground it. We charge it, then we discharge it. But we're going to discharge this through my graduating class. So everybody who was in school with me, we're going to make a big circle, and we're going to discharge this Leyden jar through ourselves. Chalou, Jan-Hui, Clement, Conquer, Jan, Fari. No. Who do you think's going to close the loop? All right, so we need... Come on, everyone, we're going to make a big circle. When we hold hands, do it very lightly, otherwise you can't feel the zap. We're going to do this experiment twice because I think other ones of you are going to want to participate. I'm going to first charge this electrophorus with my hair again because it's been working. But then I want to let somebody try to do it this way. Charge up this PVC pipe by rubbing it with fur. So we'll try that second. But it's always best to do a demo you know works the first time. All right, so we need to make a circle. Right. Start filling up. Come on, a circle, a circle, a circle. Who wants to be ground? Should it be Professor who? Sure, it could be Professor who.
Oh, it is?
No, you stand here. So this is what we do. You guys hold hands just very gently, fingertips. But Chalou, you hold Jen's hand, but not Professor Who's. Okay. So what we're going to do is we're going to charge up that Leyden jar, and then we're going to discharge it through that circuit of my classmates. We've done this with 20 middle school teachers. They loved it. We've also done it at a local science museum for children. Oh, that's a good one. I should be doing it over here. Oh, I'm short. You got to bring it down here.
All right.
Okay. Not the world's best setup, but we'll manage. I could hear that. That's good. Want to make sure we have really good zap. Yeah.
You're a professor and you have some point to both, but you feel.
All right, let's see if it works. So, Chalou, you're going to touch your finger to that nail. And hopefully everyone...
Get ready? You're talking. Let's ready to see what happens.
Oh! Did you yes! Okay. So, I got to go brush my hair. We have just a few more things to try out up here. And hopefully you're all going to go home and do this with your kids, with your neighborhood Girl Scout and Boy Scout troops. Oh, I'm going to use that. No, we are going to use this. So there's two things left. The first is to really show people visually the concept of an electric force. We're going to use this balloon to separate salt from pepper. It's a very nice demo, which only the people sitting in the front will be able to see. And then what I'm going to invite you up to do is I have several Leyden jars up here and different ways of charging them with the PVC pipe or with the plate. I'm going to invite you to come up here. Like I said, I have at least 3 Leyden jars up here. I invite you to try these things out for yourself. And I expect you all to take advantage of that opportunity. Okay, so this is how you separate salt from pepper. Let's see, who hasn't had a chance to do a demo and wants to?
Eli.
Okay, come on up. Okay, so what I'd like you to do is open a packet of pepper and put it on here, and then mix in an equal amount of salt. You can use this pen, and he doesn't have that much hair. So Jen, could you rub this on your head and get the balloon nice and charged up? He's done this. He did this at his house the other night. I know it works. Yeah, make a nice big pile. Lots of salt in there.
I should try this with my kids.
More salt. Definitely more salt. Whoa! Well, I went a little overboard, but that's fine. Okay, so, let's have maybe about 6 people can come up and see this. A couple of you come. Where's Margaret? Margaret who? Is she in here?
Okay, should be charged.
Okay, so you're going to separate salt from pepper by holding the balloon about yay high above that mixed pile of salt and pepper.
This side.
Uh-oh.
Yeah.
Oh, there it goes. Oh, wow.
Okay, let's look at what's on the balloon.
Okay.
Let's look at what's on the...
Pepper.
Okay, why did it pick up the pepper but not the salt? It's not even that complicated. Pepper's lighter. So we've got 2 forces. Both of these get polarized in response to the charged object above. But so the electric force is pointing up. The gravitational force is pointing down. The pepper's lighter, so the electric force wins. The salt is heavier, so the gravitational force wins. So this is visual. Kids can actually see this. So now I've got PVC pipe, which you can charge up, and then charge a Leyden jar, another Leyden jar, another Leyden jar. We've got these guys. Everyone, come up and play. This is not a game. Come up and play. Make me happy.
Very good.
Oh, come on. You're all chickens. Come on up. Klaus is coming up to play. He's got children.
I'll give it a shot. Yeah, this was the last slide. Yeah, so whose accessories are there? Yours?
I think this is for
Citrus?
This is for this one.
Jen?
Mouse. 但是你没有送礼具，如果不不用了。
So just turn off everything, or just put it to sleep.
Yeah, just put it to sleep.
There's the contact, which means
So there's actually 2 computers in here. Yeah, just in case. And then this is our cord, right? So Charlotte's already down there. And then when you go down, they should know that you're coming with a projector for the projector. And then you have your microphone.